happening, then let me go ahead and start by introducing our speaker today. So our speaker today is Kimmy Wu, and Kimmy has been working on the CMB for some time. She got her degree from Stanford, and then got prestigious postdoctoral fellowships first at Berkeley and then at Chicago. And then she said, "Well, it's too cold here," so she decided to move back to California, where she's currently a Panofsky Fellow at SLAC. But starting in the fall, she is going to be faculty at Caltech. And she also just very recently received the DOE Early Career Award. And she's actually going to be telling us the reason why she received the Early Career Award. So she's going to be telling us about the great work she's doing with cosmic microwave background and machine learning and field-based inference. And so it's kind of the confluence of a lot of hot things right now are happening in Kimmy's research. So this should be really fun. So please take it away.
Thank you very much for the very kind introduction, and thank you for coming to this talk. So I'll be talking about testing insulation and the standard cosmological model with CMB data. Can people at the back hear me? Because it doesn't sound like my mic is working.
Like it's not, okay. Maybe Zoom can't hear it.
But can people on Zoom hear? This echo does not sound good. I'll assume they are fine.
Oh, there.
No one's. Okay. All right. So just a brief outline of this talk. I'll introduce inflation and the CMB, and also in particular CMB lensing. And then I'll talk about improving constraints on inflation from using BICEP Keck data through delensing and some ongoing lensing measurements from SPT and the delensing expectations we can get from this data set. Then I'll talk about evasion analysis of SPT data and the cosmological parameter constraints. In particular, in terms of the sum of neutrino mass, how excess lensing connects to this negative sum of neutrino mass expectation that we see in some of the works last summer. And if there is time, there can be some discussion of the latest DESI DR2, Y3 result or X result as well. That's fresh from last week. All right, without further ado, my observable is the cosmic microwave background, which I'm sure many people are familiar with. In particular, it's sensitive not just to physics before the CMB was formed at recombination, so early time physics, but also late time physics, because the CMB serves as the backlight to many of these processes that happen throughout the course of the evolution of the universe. In particular, I'm focusing on the gravitational lensing effect of the CMB. So in terms of the early universe part, I want to probe inflation and its expected signature from gravitational waves. I hope people on Zoom can hear.
Yes,
we'll see.
they can.
Oh, okay,
Thank
great.
you. Sorry, I was just double checking.
Okay, great. Yeah, people can hear. So I'm looking for primordial gravitational wave signatures on what we call CMB B modes, which I will explain in a couple of slides. And for late time physics, I look to constrain lambda GM++ models using both the primary CMB and also CMB lensing. Connecting to the two is this idea called delensing, removing the lensing signature on the lensed CMB. All right, so inflation. Inflation generically predicts that there should be primordial gravitational waves, and BIMO polarization is the window to it. So I'll explain that in 3 simple steps from left to right. So from your GR and inflation class, you know, if you have any perturbation of the metric, you can decompose it into tensor, vector, and scalar perturbations. The vector perturbations in simple inflation models decay, so we can ignore it for this standard scenario. The tensor perturbations through inflation get stretched out into classical gravitational waves. So these red and the blue arrows signify stretching and squeezing of space-time. What that means is that during recombination, you have baryon photon fluids. So what it means is that they redshift and blue shift the photons. So if you're an electron in the center of this frame, you see a quadrupole of temperature and isotropy of hotter and colder photons, which introduce a polarization in your CMB. Now, similarly, scalar perturbations, essentially these are like pressure waves, and they are the seeds for a structure formation. So if you have a sound waves traveling through that baryon photon fluid, then you have hot and cold photons in this path, and if you're an electron, you also then see a temperature anisotropy, quadrupole temperature anisotropy that acquire polarization as well. It turns out then with the gravitational wave stretching and squeezing, one way for us to describe CMB polarization is through these E and B bases, E modes and B modes, where E is curl-free and B is divergence-free. So gravitational waves produce both E modes and B modes, while scalar perturbations, these density waves, can only generate E modes. So if there's no primordial gravitational waves from inflation, we don't expect to see any B modes on the CMB at recombination. So that motivates us to look for these B modes. So for the rest of the talk, I will be using R, which is this tensor-to-scalar ratio number. And essentially it just compares the what is the amplitude of the tensor perturbation spectrum compared to the scalar perturbation spectrum at some Privet scale. If R is like large enough, then that in simple single field slow roll inflation models, that will mean that the potential of inflaton is close to kind of grand unified theory scale physics. So being able to measure this parameter could allow us to probe some of the phenomenology at the highest energy scale that we can probe in our universe. So that's very amazing. In particular, if you want to work out various phenomenological relationships for potentials and various potentials, and also whether there are like different shapes of the potentials, you can make a plot such as this. So this is R on the y-axis, and this is n sub s, which is the tilt of the scalar spectrum on the x-axis. So inflation, inflation predicts that n sub s should be slightly smaller than 1. That's well confirmed from Planck data already. And different inflationary models will predict different combinations of R and n sub s. So being in this space, being able to rule out classes of models that predicts different combination of R and n sub s. And for example, in this orange band is one of these really popular textbook models of inflation potentials. That's pretty well disfavored at this point. But then if you say, for example, shift n sub s, that can kind of rule in and rule out and be flexible about this space and see what happens. All right, so that's some of the theory motivation of why we want to go after B modes in the CMB. And so now let me spend a few slides to discuss what are the challenges of this measurement. So in CMB, we typically go with the summary statistic, which is the power spectrum of our anisotropy in temperature, E mode, and B mode polarization. So effectively, what you measure is your full sky map or partial sky map, and then you do a Fourier transform, and then for the same L modes, you bin them, and then put band powers on these lines. So just from this plot, temperature anisotropy is very well measured. E mode polarization is getting better and better measured. B modes is essentially not well measured at all right now, but just this is on log scale, and for R equals 0.1, this is more than 5 orders of magnitude smaller than the temperature anisotropy power, and then compared to the mean of the CMB temperature of 2.7 Kelvin, these fluctuations is 1 part less than 1 part in a million. Those are very faint. And from the BICEP Keck team's upper limit, R is less than 0.036, so it's slightly below this 0.19. And one thing that I'd like you to pay attention to is that this peak is about L of 90, which is about 2 degrees on the sky. And for reference, the size of the moon, the diameter of the moon is about 0.5 degree. So we are looking for fluctuations that's kind of up and down for a few moons, okay? And that has relevance for how we design our instrument. So that's first challenge. These are very faint signals. Second challenge is this already are drowned under galactic foregrounds. So for the BICEP patch, which is a very small patch kind of out here in galactic coordinates, which is already very far away from the galactic center in the galactic plane. This is the foregrounds at 150 gigahertz. Mostly this is dust on the cleanest-ish 1% of the sky. That's already above our current upper limit. So galactic foreground we have to deal with multi-frequency observations and some model of the SED of each of these components, both galactic thermal dust that's polarized and also synchrotron emission. Then, let's see, I think, yeah, okay. Then another source of confusion for B modes comes from CMB lensing. So the idea is that the CMB adds recombination. The photons get emitted and they travel all the way to us. And in between us, there are these gravitational overdensity and underdensities, and these gravitational potentials deflect their path. So what we observe is a lensed version of the original fields, and the amount of deflection is encoded in the gradient of this phi field, phi being the CMB lensing potential, and it is a rated gravitational potential integrated along the line of sight. In pictures, this effect looks like this. For temperature, E mode, and B mode polarization, assuming no primordial B modes at the bottom panel, note that 3 different color stretch for T, E, and D. So you see that there are deflection of these modes for T and E, and then lensing also generate B modes. Now, I'd like you to focus on this bottom panel, where I'm going to overlay R equals 0.1 fluctuation. And for scale, these are 8 degree by 2 degree simulations. So I hope that you see like a large scale modulation over the small scale fluctuation of the lensing B modes. Yes, no? Yeah, yep. All right. So R equals 0.1 is already way above what our upper limit says. And then on top of it, there is like galactic foregrounds. So that's kind of like the challenge that we are facing. And power spectrum level, this is what the power of lensing B mode look like. And this is already a key source of sample variance in our measurements. Okay, so and we did delensing for that. Now, I described lensing as like this contaminant to the R measurements, but as many of you know, person A signal is person A's noise is person B's signal. So in this case, phi is also in the same category. Phi itself, the CMB lensing potential, can be well used to constrain lake time. In this case, kind of redshift 1 or 2 physics, where the CMB lensing redshift kernel peaks. In particular, is sensitive to matter density and structure growth, and can be used to constrain, for example, some of neutrino masses and various dark matter models. So this is an illustration of the suppression of the CMB lensing power spectrum given different sum of neutrino mass. Because, for example, neutrinos, they below their free streaming scale suppress structure formation. So with heavier neutrinos, you expect more suppression of the lensing potential power spectrum. So this can be a signature of a way for us to be sensitive to some of neutrino mass. And also with the lensing power spectrum can be used to test consistency within lensing CM model across redshift and scales. That could be interesting for the ongoing discussion and discourse about the Echelon tension and the SA tensions. One thing that I'd like you to take home from today's talk, if nothing else, is that the CMB lensing measurement is now at high signal to noise. So these are the 3 premier CMB lensing measurements we have in the field from the Planck satellite, from the Atacama Cosmology telescope, and from the South Pole telescope. The red, yellow, and blue boxes are the band powers from the 3 experiments. The signal to noise of each of their individual measurements are at the around 40 sigma level, and then combined together, it will be around 60 sigma. Is a project two postdocs at SLAC and Stanford are leading. And what that means is that it actually can provide competitive cosmological parameter constraints to the primary compared to the primary CMB. So it's amazing to me because 10, 15 years ago, like this is a new measurement. Like it was 10 sigma, 20 sigma, well, 10 sigma, kind of below 20. I remember seeing the first CMB lensing paper. It's like 4 sigma detection. And it was not useful for cosmology. And now this could be a new tool to really nail down some of these cosmological parameter and sensitive to later time physics compared to the primary CMB. To be more specific, it is now competitive in terms of this lensing best constraint parameter, sigma 8 omega m to a quarter to primary CMB. And if you combine with BAL, sigma 8 itself has similar uncertainty from primary CMB. And on the right here, I'm showing SPT3G survey footprint. I'll introduce SPT in a moment. But the red, yellow, and green patches are the surveys that we have conducted already, and it covers about 10,000 square degrees on the sky. And with data in the can already, we predict more than 100 sigma measurements of the CMB lensing power spectrum. So that's a 1% measurement of this signal. What that means is that we'll get a few times tighter constraint on SA, and that will be important for the H0 tension discussion through its sensitivity to the matter content. All right. So before I discuss any of the results from BICEP, Keck, and SPT, I must introduce the two telescopes that I used the data for. They both observe at the South Pole, and they provide complementary information of the CMB. The reason why is because of their different instrument design. The BICEP Keck telescopes are what we call small aperture telescopes. So one of these receivers that is hidden, this is the four baffle. The receiver is actually below it. If they are small, these are refractor telescopes, and the resolution is low actually for CMB standards. Each of their resolutions around a quarter degree. So just sufficient to resolve the 2-degree bump that I mentioned at the R equals point in the power spectrum plot that I showed. And the different tubes have different frequency coverage. So that's important for cleaning galactic foregrounds. For SPT, it's a very different style telescope. This dish is 10 meters across. Folks who work with BHT here is probably familiar with SPT, and I saw Dan in the audience. The receiver sits in this cabin, and this is the detector array observing at 9150 and 220 gigahertz. And because of the 10-meter dish, we are able to achieve an arc-minute resolution at 150 gigahertz. And that's important for CMB lensing because for CMB lensing, the way that we do the reconstruction is that we use the small scales in the CMB to reconstruct the lensing map, which I'll discuss in a moment. And I'd like to also acknowledge folks from both collaborations for contributing through the whole from instrumentation to data processing through the maps to this work. So a brief summary of just the introduction part. B-modes provide a unique window to early universe physics, and we need delensing to reduce impacts of the lensing B-modes on primordial B-mode measurements. And by measuring the lensing potential phi, we can constrain cosmological parameters sensitive to matter density and growth of structure. Now, both lensing and delensing is possible and exciting because of the high signal-to-noise measurements of telescopes at the South Pole. All right, so I'll talk about delensing these BICEP Keck B-mode maps. The idea is quite straightforward. So I mentioned these lensing B-modes come from lensing of B-modes, of E-modes. So if you have an E-mode map, you have a phi tracer, your CMB lensing potential. So this is a toy 2D Gaussian. You can compute what your lensing B-mode look like. And if you have your lensing B-mode template, you have observed B-maps that has convection dust, noise, and potential primordial gravitational wave generated B-modes. You can form auto and cross spectra of these guys and have expectation values set given theory. So how much lensing there should be, how much R there should be in all of the auto cross paths. and be able to, in all likelihood, derive what each of the parameters are. Okay. So in our first demonstration, using some of the existing data, we use Planck's cosmic infrared background map as a phi tracer. This is an illustration. This is a CMB kappa on the same field. This is a 500 micron map in the back color. So you see pretty high level of cross correlation between the two tracers. For the EMOT, we combine BICEP Keck SPT pole and Planck. And this is what the 2D Fourier fluctuation power look like. And this is a combined version. Yes.
Sorry to bug you, but can you tell me where the lensing signal comes from? I gather that you're able to measure it, but I don't know how you sense it and deduce what it is.
Yeah. So that is after. Yeah, I started the talk with delensing, but actually in the next part of the talk, I will actually introduce the lensing estimator. The lensing potential here, this is just the cosmic infrared background that is a tracer of phi. So this is just light, infrared light that is re-emitted from dust around star-forming galaxies. So star-forming galaxies emit a lot of UV, and UV heats up the dust, and then dust re-emit in the infrared. So this traces the higher redshift star-forming regions, which overlap with the lensing potential redshift kernel really well at like a 60% level. Yeah. And I mentioned autocross spectra and likelihood a while back. So how do we do this analysis? So we observe on this patch, we have maps from BICEP Keck and also WMAP and Planck important for dust and foreground modeling. Without delensing, we just take all of these maps and form auto and cross spectra. With delensing, we input also what the lensing BMO template look like. And now with, this is kind of a mosaic of all the auto cross spectra, and you don't need to look at all the points because that will make you very dizzy. So I just focus on the 95 and 150 auto from BICEP Keck as an example of what the band powers look like. And we fit a 7-parameter foreground model with also lensing BMO power and R to all of these auto and cross spectra. Now, without delensing, this is what the posterior look like. And now as a moment of exercise for you all to decide what will happen after I include the lensing template. So there are 4 options. There could be shift of the location of the peak and also change in the width of the posterior. So option A is you have reduced uncertainty, so narrowing of this width and also shifting of peak to lower R, and then the 3 other combination. So I'll give you a minute to think about what your answer would be for A, B, C, and D. You don't need to raise your hand. Once this minute is passed, you will learn what the answer is in the real universe. You can also discuss with your neighbor.
If it's statistical, it's statistical, or it's natural.
Yeah, I was thinking about that. That has to grow. But
I'll see if you know exactly what it is.
I'm very happy to see the engagement here. So let's find out what the answer is. Okay. So this is without delensing. This is with delensing. So the upper limit got shifted down a little bit, about 10%, and this is still, it was the first and still the only analysis that improved uncertainty on cosmological parameters with delensing. So if you're curious what the answer was, it's A. The width of this uncertainty got reduced and the peak actually got shifted down a little bit. From simulations, we find that there's about 30% probability that this data set will get a higher peak R. So you could have been correct if you chose B as well. Okay. All right, so current limitation to this exercise. Bemal variance in the particular previous data set was not dominated by lensing, but then in our latest result in BK, what we call BK18, lensing is already the dominant source of uncertainty. So the lensing on the current data set will give us a fractional improvement on a larger fractional improvement on sigma r than the previous data set. We need a better phi tracer. The CIB map is good, but it's the cross correlation is at the 60 to 80% level. A CMB derived phi, which I'll discuss in a moment, should do better. All right. So a phi other than CIB. So this is work with Yuki Omori, Yuka Nukato, and Federico Bianchini. All right. So how do we get the phi from lensed CMB map? The idea is quite straightforward. So without lensing, angular multiples at different L of two maps should average to 0, where X and Y here is and CMB are TE and B map. But then because of lensing, the correlation is introduced across L's are proportional to the phi power. So you can essentially then construct an estimator that have two CMB input map inputs with relevant weights to get what phi look like. And that is trying to address your question.
Sorry, what is the variable L?
Yes, that's the angular multiple. So if you have a map, you Fourier transform.
Okay.
Yeah. And big L, we just use it to denote the angular multiple for lensing field, which is not the directly observed field, whereas X and Y here are directly observed.
So sorry. So is this because the X and Y are Gaussian?
Yes. So we the CMB unlensed CMB are very well approximated by Gaussian random fields, and we still have not detected primordial non-Gaussianity. All right. So an example of a quadratic estimator for just say if you have input CMB T maps is looks like this. It's actually really simple. You have your two copies of your CMB T map. You take the gradient of one of them, take the product of the two of them, and then take the divergence, and that gives you phi. That's it. Obviously, in the actual analysis, there are a lot more details to go in, but conceptually, this is like a match filter. And this is an example of what in simulations, what the input kappa map look like. And this is a TT quadratic estimator reconstruction, given some noise level of the reconstructed kappa. From CMB, from SPT3G 2019-2020, like 2-year observation, this data set, we make, this is a preliminary CMB lensing convergence map. And this map is really amazing to look at if you're new to seeing these maps. I love looking at this because these are high signal to noise. And it will be the highest signal to noise map of the projected mass of matter over and under densities for a while. What that means is that each of these modes you can see by eye signal to noise of a few. And so if you go to that RN deck on the sky, the integrated line of sight, what you see as an over density here is a true dark matter, total matter over density. In terms of cosmology, this is a forecast using the CMB lensing only measurement. So without adding BAO or primary CMB, I have said that this parameter combination sigma 8 times omega matter to a quarter is what's CMB lensing best constraints. From the Planck measurements and the XDR6 lensing measurements, they both constrained it at the 2.7% level. This particular measurement from the 2019-2020 data set, we are talking about an almost factor of 2 improvement in the uncertainty. So this will be competitive to uncertainty from Planck primary CMB, which I'm very excited about given the current state of the discussion on SA tension. Now, how useful is this map for delensing? So you can calculate the cross correlation of your reconstructed phi with your input phi. How well the E mode is measured is a subdominant factor. So essentially, you can compute the cross correlation of your phi tracer. That gives you to the ballpark of how well it can delens. This is for the Planck phi map. This is for a CIB map that I showed you in the earlier part of the talk. This is kind of our initial first year data set cross correlation. The map I show you will sit somewhere higher. So it is already better than a CIB for certain scales. For the final depth for SPT3G, we expect it to just be much better compared to any other tracer that we have. Okay, so this is an example of the lensing BMO template given our given the Kappa map I've shown you. So the Kappa map is from 2019-2020 observations, and we use E modes from the same set of observations. And this is from simulations a template, so you can compare it to the input BMO map and see how well they match each other. All right, so this is the simulation input. So by eye, you see that where there's positive structure in one, also traces a positive structure in the other reasonably well. The actual cross correlation is about 60 to 70%, which means that we remove about half of the lensing BMO variance. And a separate discussion on contaminations from extragalactic foreground biases. I don't have time to talk about foregrounds and contaminations on the phi measurement, but we have quantified that should be negligible. The expected improvement on uncertainty of R of this measurement, this is our latest, BICEP Keck's latest sigma, it's about 0.01. Without delensing, this curve will plateau with some introduction of new receivers on the BICEP array side. With SPT3G delensing, we expect a factor of 2 to 3 improvement on the uncertainty of R. So what that means is that it can rule out R of kind of 0.01 models at 3 sigma. So some key takeaways for this part of the talk is that the 3G 2019-2020 data set will deliver the deepest CMB lensing map ever made to date. I'm really looking forward to this result out, and hope we'll stay tuned. And the lambda CM parameter uncertainties from this lensing map will be unprecedented. I'm very excited about that. And this lensing map will be used to input for a lensing BMO template for delensing BICEP Keck data, and we expect it to remove almost half of the lensing BMO power. Now, the next part of the talk is about field level inference and how to and some of the latest cosmological results from SPT. And to motivate that, I want to discuss why we need a beyond quadratic estimator lensing, especially in polarization. So and the example I use as temperature, we have 2 temperature maps. I haven't really discussed polarization map, but this is a plot of the lensing power spectrum signal in the gray. And then in the orange is polarization lensing map noise reconstructed from polarization map. And then the blue is lensing map noise reconstructed using temperature maps. So if your CMB map noise is at 10 micro-K arc minute, some CMB people units, okay, the temperature reconstruction has better noise compared to the polarization. But then if your input map noise is 10 times lower at 1 micro-K arc minute, your polarization reconstruction for lensing map is actually much better. And the reason for that is actually because of the sample variance from your lensing B modes. So in the pair of maps that's E and B, if your B modes, you can avoid a lot of the sample variance that come from the B modes because it's lower. And in particular, we know that for the quadratic estimator, it is the signal to noise is slightly suboptimal below if your noise level is below 5 micro-K arc minute. So a field level likelihood based method can circumvent this limitation and allows us to get even better than what this line says for phi. And that's what we did in this really latest result from SPT using field level analysis on this data set, but just on polarization. Also, this is work led by Fei and Marius. Also, the likelihood of this is available, publicly available, so feel free to play with the chains and combine with your favorite data sets. So in pictures, how this field level forward model analysis work. We have a simulator. In this particular analysis, we simulate unlensed polarization maps. So these are Gaussian random fields given a power spectrum of EE and phi, and CL phi as well. So we model lensing, and you have lensed polarization map and in EMB. So this is a simplified picture. We also model systematics and noise and so on and so forth. Now, with a bunch of, you have a simulator, then you have your analyzer. So you have some data, and in this example, it's just a noiseless data, right? Very simple. What we compare is a compressed statistics from this two set. Run many simulations, compute this compressed statistic, do that once on data, and essentially you find the sets of simulations that have matching compressed statistic between simulations and data, and find the best fit parameter. So input data maps are the TQU maps, and these are the best fit kappa, CMB lensing convergence, and unlensed E in data. And these are what the band powers look like given these maps. This is a very busy plot, but the black points are from SPT. This is the phi band powers. This is the E mode, unlensed E mode band powers. So for the scales that are quoted within these red arrows, these are the tightest measurements of that angular scale range to date. What that means is that SPT is superior in probing these smaller angular scales compared to other experiments. And in phi in particular, we are probing into slightly mildly nonlinear regimes in K-space. We are able to provide pretty stringent constraints on lambda CM parameters compared to other data sets with polarization only data. So in blue is our 1D and 2D contours posterior in H0, Kodak meta density, and baryon density. So we are in blue is SPT, orange Planck, and gray is ACT. This is actually the first evidence or / confirmation where Hubble tension exists, also in polarization only measurements of H0 between the Schultz inferred H0 and ACMB measurement. Including TTTE from the 2-year data set will give comparable or better lambda CDM constraints and Planck. So I'll show a forecast in a couple of slides. So I want to talk about neutrino masses because it's interesting, and that's something that lensing is particularly powerful in constraining. From this data set with CMB only data, so this includes primary CMB and CMB lensing with Planck, ACT, and SPT. We set an upper limit on mu to be less than 0.2 eV. So that's good and well. But then once you combine with BAO, this is DESI Y1, but the picture didn't change very much, and MK can update the exact number. You get a very tight sum of neutrino mass upper limit that's putting pressure on the inverted hierarchy of neutrino mass in lambda CDM. And over the last summer, some folks are opening up the sampling for neutrino mass to allow it to be negative, and they show that the preference for there is a preference for the peak of the posterior to peak at a negative sum of neutrino mass, and they conclude that it's because of excess lensing. Okay, but is it really excess lensing? So let's think about what that means. So excess lensing is a statement relative to the measured lambda CDM parameters. So how well are each of these parameters measured? In particular, if you look at this plot, so this is a lens parameter. So it scales the CL55 plot and propagates its effects into the primary CMB as well for a different data set combination. So everything in the red box include BAO in the determination of lambda CDM parameters. Without BAO and it's just CMB, whether it's Planck, ACT, or a combination of or SPT, a combination of two or the three. So you see that there is a trend of preferring a higher A lens, so more lensing than expected when you include BAO. So yeah, if A lens higher than 1, you have some excess lensing than expectation. One thing to point out is DESI BAO, both Y1 and Y3. So here in the green is the Y1 error bar, the Y3 DESI is the central value is similar, shifted a little bit. The error bars are about factor of 2 tighter. So I just hand drawn it in this plot to show that. It actually prefers significantly lower omega matter compared to what CMB measurements in the blue show and supernovae measurements in the orange show. So in particular, if you combine CMB with supernovae measurements as like an omega matter anchor, the negative neutrino mass preference disappears. So my personal conclusion is that more data will probably further increase or decrease increases statistical significance of any of these statements, and it will be interesting to see what might come. So I promise a forecast of how well we'll do in some of the subsets of the lambda CDM parameters when we combine the lensing measurements that I showed in the earlier section of this talk with the TTTEEE primary power spectrum measurements from that same data set. Because in the points I drew, so in just the previous slide, we just have unlensed EE, but not TT and TE. So including TT and EE, we'll be able to extract powerful lambda CDM constraints, combining with both primary CMB and lensing. In particular, the uncertainty on H naught will be about 0.6 kilometers per second per megaparsec. And this is from just CMB data. And that's a sub% level constraint within the lambda CM model. And that's shown in the red lines. And the blue line is what the polarization only field level inference results are. So we improve that significantly in the baryon density measurement. And with the red, we are kind of in the comparable space as Planck and XGR6 H naught. So this is a summary of the talk. Lensing B modes are one of the foregrounds of primordial B mode measurements, and it's a dominant uncertainty of the latest R measurement. We have demonstrated a reduction of sigma R when delensing BICEP Keck maps. And looking forward, delensing BICEP array maps using SPT3G lensing of potentials will improve sigma R by factor of 2 to 3. And SPT3G CMB lensing, so this is the kappa map from that analysis, will provide a 1.5% constraint on sigma 8 omega m to a quarter. So that's almost 2 times better than existing measurements. And combining our lensing measurements with our primary CMB spectra will give competitive H naught uncertainty. And very curious preference for negative neutrino mass is intricately linked to excess lensing, and future measurements will further illuminate this issue. And I have a couple of slides on DR6 and DESI Y3, but I will kind of leave that depending on if there is interest and conclude. No, thank you.
Todd?
So, pardon this question. There's a lot of things I'm trying to disentangle. So if I understand correctly, you're using the emission of hot dust or even cold dust produced by galaxies to trace the dark matter halos. But of course, it takes a while for the dust to be formed and lit up and everything else, while the dark matter is, growing essentially from the start of the Big Bang. So the questions are, is there a particular redshift sensitivity to where the lensing happens so it doesn't matter? And with that, if I can stack on one more thing, it was intriguing to me that you sort of discarded the CIB information for even longer wavelengths. And I was wondering during the talk if the newly launched SphereX, would give you distributions which would help you understand the lensing better than what you could do from the microwave.
Right. Yeah, so I think, I don't have that plot in the slide deck, but yeah, so if you plot so you have as a function of redshift, and then this is kind of like the redshift lensing root for CMB, redshift lensing kernel, it peaks around like 1 to 2. And then, so that's where kind of star formation.
So you're very lucky that works out.
Yes.
You have the most
Yeah,
extensive star
yeah.
formation. Okay.
Exactly, and that overlaps really well with the CIB, it turns out. So CIB is actually really good as one of the best kind of tracers. We can also use galaxies as the dark matter tracer, but then typically galaxies, for the surveys that we have in hand, they don't go beyond much past redshift of 1. So we can, there are definitely forecasts with using galaxies as also the phi tracer in addition to the phi reconstructed from lens CMB, and then how much that might improve the delensing for B modes. And I think for SPT3G, it will still help a little bit for sure, especially for our existing data now. In the next 3-4 years, once we have accumulated even more data and the CMB map itself is deeper, the added value for adding the galaxies or other tracers will diminish a little bit. But right now it will be quite useful actually.
Do you think you will get help from SphereX?
Yeah. For SphereX, because the field that we overlap with them is on their Y field. So they do have good galaxy density. And I think it will be similar to, because for the way that they find galaxies is based on existing surveys. So I think that will be similar to what we can get, for example, from Euclid, which we also have very good overlap. And their data is also coming out. And we have but we have MOU with both SphereX and Euclid as well. So those are both good partners to use external tracers.
Yeah, I just wanted to express my interest in your hidden slides here.
My what?
Your hidden slides.
Oh, I see. Yeah. Extras. Yeah. This is a fun slide. This is some of neutrino mass. The yellow I mentioned kind of in a bullet point about using different essentially constraints, using different parameter combinations. In the blue is just CMB. So this is Planck and X with X lensing and Planck lensing as well. This is from the latest X result from DR6 released from last week, and we have already combined ours with them, but I'm not allowed to show that yet. The L here. Oh, sorry. Right. So this is actually just primary CMB. This is no lensing. L here is lensing from both X and Planck. B means BAO. And then the purple B is DESI BAO. The light blue B is BAO from BOSS. And S is supernovae. So the my takeaway from this plot is that so this is the 0.06 EV line. So that's the limit from normal hierarchy. And then this is the 0.11 EV line, which is the inverted hierarchy limit. My takeaway of this slide is that we still get with this purple line, we get negative neutrino mass preference if you allow this to go negative. Effectively because the BAO from DESI is will pressure your omega matter to go lower compared to what CMB prefers. What that means is that your lambda CDM predicted CL55 spectrum will have some power that is slightly lower compared to where your band power sits. Plus there is an excess lensing, and the excess lensing, because what neutrino does is suppression of structure formation, this does the opposite. Thus you have a what phenomenologically is like a negative sum of neutrino mass. And we can think of it as excess lensing. For the supernovae case in gold yellow, supernovae prefers high omega matter. So when you fit that with CMB data, the expected lensing power spectrum has more power, and your actual measured band powers is kind of low compared to your expectation. So when the model try to fit and there is a free parameter of neutrino mass that you can tune, it just says that, oh, there's more sum of neutrino mass. Thus, your model would now fit your band powers. So the peak of the posterior peak positive. So I think that's quite interesting. Let me see if there are more. Oh, I can't see. Yeah, Y3 measurements. More discussion. But yeah. This is really fun.
Mhm.
Yes.
When you give sums of neutrino masses, is there a prior that there are exactly 3 generations?
Yeah, to go back to what is in the assumption in the Boltzmann code, typically, yeah, I can't say for this particular analysis what their assumptions are. Yeah, but typically we assume three neutrinos, and then I think one of them massive and 2 of them massless. But then for kind of this range of cases, they could have done slightly different parametrization where all the masses are kind of like equal in all 3 species. This is a detail that I do not know. Yeah.
So you showed the posterior on R before and after delensing.
Yes.
So the posterior shrinks, but I would imagine if you're delensing with a template that is not perfect, like you showed, like the correlation coefficient does not exactly trace the gravitational potential. If you fold in that uncertainty, shouldn't the posterior broaden instead of shrinking?
Yeah, that's a good question. So that this enters kind of the modeling of that work. So the way that the lensing template is constructed is because the input maps are Wiener filtered. So the lensing B-mode template, you can think of it as a Wiener filtered B-mode as opposed to B-mode where you have the signal that matches the lensing lambda CM B-mode and kind of exploded noise. So the expectation, effectively, if you're doing it correctly, the uncertainty should always decrease.
We have a question from Zoom, so I'm just gonna read. Recent reports from DESI indicate that dark energy has weakened over the past 4.5 billion years. Is there anything to link this to the observations of the CMB or the very time-limited inflation?
Yeah. So actually, I think so what CMB is sensitive to. So for primary CMB, we have like the peak location of the peaks. So essentially, it tells you the angle of kind of the sound horizon at recombination. So it's so that we measure very well, and we know the angle. We know physically, we can calculate physically what is the expected diameter given the baryon and matter. Measured baryon and matter given the location of the peaks. Now, we then determine the energy densities of different species. Given different model, if it is lambda CDM, you have the cold-dark matter and baryons already. Then if it is a flat universe, then you already determine what is omega lambda. Then you can measure you can get the distance. So very much if it is not a lambda CDM, let's say there's WA, non-standard WA and W naught. All we are sensitive to is kind of this distance, and you can kind of change things in ways that compensate, and CMB won't really notice, not primary CMB. And then for CMB lensing, because of the sensitivity of the redshift kernel, most of it kind of come from 1 and 2. And dark energy really kicks off kind of on this lower redshift bit. We have some sensitivity to it, but I wouldn't use CMB lensing to constrain dark energy models. So yeah, that will be that's actually why if that's, I'll take that back. No, yeah, I thought I had an insight and it's not.
An unfair question, Kimmy, but it's a small room and no one's gonna hold you to this. How do you think we're ever gonna get out of this mess, which is just another new mess? We have people working as hard as they possibly can on multi-year experiments and independent teams, pursuing every approach to its end, and when you bring them all together, they fight. You know, the answers disagree. What do you think is going to be the escape hatch? It's not just this, right? The Hubble fetch is another example. Yeah.
Right. Yeah. It's very hard. Yeah. It's. I don't have a good answer to that.
That's why it's an unfair question.
Yeah. I think it encourages a lot of good kind of creative theory development. Actually, like with the Hubble tension, I feel like every generation then understand the lambda CDM model better because of these cracks. Because otherwise no one's gonna go back and study the lambda CDM. And now I feel like I have a better handle on dynamical dark energy because of these results. Like, oh, okay, now what kind of data would I want to go out and measure to try to get a better handle on this, right? And for example, for H0 tension, we have the gravitational siren that is completely different compared to like the local distance ladder measurements versus CMB or BAO only. BAO, we have BAO plus DESI kind of H0 measurements as well. So I think many times these tensions we see definitely encourages the experimental group to work harder to look deeper into what sources of systematics there may be. But at the same time, it also encouraged theory folks to develop new ways to kind of make everything in concordance. Yeah. But yeah, it's a very hard problem. I think we all kind of do our best.
Yeah.
Yeah.
It's job security. Maybe.
Nothing is.
All right. Let's see. Any last questions? If not, let's thank our speaker one more time.